Okay, now today we are going to solve a geometry problem which appears in the Chinese Mathematical Olympiad in 2013, and it is placed in problem 1. Actually, in almost all of the mathematical Olympiads, the problems which are placed in the first are relatively easier than the others. So this isn't an exception. So it is relatively easier than the other questions in the CMO. I mean the CMO, not the IMO, because if you take a look at the CMO questions, you might find that the difficulty of CMO is as difficult as or more difficult than the IMO. So just as this question, you might find the problem, oh my god, it is too long, and if we look at the diagram, it is a little bit complicated. So how should we deal with this kind of question? So let's just learn and see. In the problem, we can see K1 and K2 are different circles and their radius are different lengths. So yeah, and this means the diameters of K1 and K2 are different. This is obvious, and that they intersect at the points A and B, and points C and D are on K1, K2 respectively, and A is the midpoint of the segment CD. So that means A is on line CD, is on the segment CD, right? That's obvious. And we extend the segments DB and CB and let them intersect the circles at E and F respectively, and assume the perpendicular bisectors of the segments CD and EF are L1 and are L2 respectively. We have to prove that. First, we look at the first question. We have to prove that our L1 and L2 can intersect. What does it mean? That means L1, L2 intersect. It is equivalent to L1 not parallel to L2, and they are not the same and different. So since we know L1 is perpendicular to the segment CD and L2 is perpendicular to the segment EF, so what will happen when L1 is parallel to L2? It's quite easy, right? That means CD is parallel to EF. So that is equivalent to CD not parallel to EF. So if this is not that easy to prove, like they're not parallel, so how can we do this? Here's a solution. We can assume CD is parallel to EF. So we try to find out what will happen. First, with like if we don't look at the like CD is parallel to EF, according to this one, A B, F, D concyclic. What can we get? We can have CB times CF equals to CA times CD and equals to half of CD squared, right? Because CA equals to half of the circle, half of the length of CD. So in the same way, if we have A, B, E, C concyclic, what can we get? We can get dB times dE equals to dA times dC equals to half of CD squared. So this will lead to CB times CF equals to dB times dE, right? So next, when we have since CD is parallel to EF, then we have, what can we have? Of course, the triangle CBD is similar to the triangle FBE. So that leads to CB over BF equals to DB over BE, right? So that is equivalent to, let me write in the next line. It is equivalent here. It is equivalent to CB over DB equals to BF over BE, right? So it also equals to what? CB plus BE, BF over DB plus BE. That is easy to prove. So what will that lead to? Of course, that is CF over DE, right? Where did I write wrong? Here it is B, not BC. So what can we get from this part here? What can we get from it? Notice that here and here we can have CB times DE equals to CF times DB. If we compare these two things, what can we have if we if we if we calculate 1 over 2, if we look at the left, oh no, we cannot deal with it like this, or maybe we try a new way. It's like that, this one. From 1, oh no, this is 1 and this 2. From 1, we know CB over DB equals to DE over CF. From 2, we can know that CB over DB equals to CF over DE. So, and that leads to DE over CF equals to CF over DE, and that leads to CF equals to DE. Am I right? So what can we have after getting the conclusion? CF equals to DE. Let us see. If CF equals to DE, these two lines. Oh, sorry. Here CF equals to DE. And then we can get BC equals to BD and BE equals to BF, because the ratio of BC over BF and BD over BE are the same. So what can we get from this conclusion? We must have like, let me copy the photo here. So what can we get from this thing? Then we can get BC equals to BD, and we have AC equals to AD. We know that BA is perpendicular to CD, right? That's very obvious. So we can know that B is on L1, right? And in the same way, we can know that B is on L2. So from here, we can know that A, B, P, these 3 points are collinear. Although it doesn't look like that on this diagram. So if we connect the points A and B, we must find that the angles CAB and DAB are all equal. They all equal to 90 degrees. What does it mean? That means BC and BD are the diameters of K1 and K2. Is it? So what can we get from that? Plus, or we can say, notice that BC equals to BD. Then K1, K2 have the radius of the same length. Right? So that is opposite to the question. So we can know that CD is not parallel. Here it is wrong. It's not parallel. How do you spell that? Parallel. Is this spelled like? Oh, parallel. Sorry. Parallel to EF. And that makes L1 is not parallel. Oh, sorry. To L2 and also different. And that makes that L1, L2 can intersect. So that's the end of the question 1. It is not that difficult at all, right? So let's continue, proceed to the question 2. What should we prove is that CA, AP, and PE. Let me mark these segments. CA, AP, and PE. Like they are the size of a right triangle. So in the graph, we might find that. What can we just seek out? What can we seek out? You might find that AP is larger, obviously larger than AC. So we try to prove that CA square plus PE square equals to PA square. So that's what we want to have. So first, let's do something with the with CA square. What can we get from that? Except we have in the problem 1 we have CA square equals to maybe half of CB times CF. What can we get? What else can we get? I can give you some hints. Like if we connect the points AF, AE, AE, and PF. Actually, PF is not necessary here when we are when we are finding the clues about AC, but it has some other uses in the when we are studying the segment PE. So what can we get? Like if I add more, oh no, that's enough. What can we get? What can we get from this picture? We can easily find out the angles. Angle C equals to angle AED, right? And also the angle AFC equals to angle D, right? So what can we have after that? That means the triangles ACF and triangle AED are similar. Is it? What can we have after that? It is AC. Oh, sorry. AC over AE equals to AF over AD. Remember that AC is equal to AD. So that means AC squared equals to AE times AF, right? That's one thing we get. So we're going to study the segments the connections between AE and AP and PE. So what can we get? What can we get? Remember that the angles CAP and DAP are all equal to 90 degrees, and from the similar triangles we can find that the angle CAP equals to the angle DAE, right? So let me mark them. CAE equals to DAE, and add also we have the 90 degrees the same. We can find out also AP is the bisector of angle EAF. Right. From here, what do we want to get? What do we want to get? We should think carefully of this thing. What do we want to have? If you can seek out that here, we want to get PE squared, and we might find that if we mark the intersection of AP and EF as the point G, here, if it is the point G, it is not that, not easy to be find out. If it's point G, what can we get after? If we have the similar triangles like PEG and PA, we must have PE squared equals to PG times AP. So we connect the segments PE and PA. Right, so that's our aim, to find out the connections between PE and PA. So how can we prove that there exists a pair or two pairs of similar triangles, PEG and PAE, and PFG and PAF? What is it equivalent to? What is it equivalent to? Of course, if you can see out, that means we want to prove that I, E, P, and F are concyclic. That's the core, that's the key of this problem. The rest of the problem. So we might paste, let's copy this one here. Here, let's copy this photo and paste it here. Why do I say the concyclic quadrilateral is available to be proved? Why do I say this? Because if you construct a circle, if you construct a circle with a triangle inside, maybe it's here a triangle, and with its angular bisector, what can we have? If here it is the angular bisector and ABCP, P is on the perpendicular bisector of BC, right? So what are the differences between the problem and here down in the diagram? That is like a theorem and its converse theorem. So we try to prove that if we have these kind of things, like P is on the perpendicular bisector of EF and AP bisects the angle EAF, we try to prove that the 4 points are concyclic. So what can we do? What can we do to prove that? If we want to prove a quadrilateral is concyclic, what are the methods? One is to prove that the opposite angles, for the opposite angles, their sum is 180 degrees, right? So how can we get the number 180? Actually, it is not easy to get. So how can we get the things? For example, one angle and 180 degrees minus this angle. What of these things is the same? What makes these two things the same? Of course, you can find out. We use the sines. So if we use the law of the sines, again, the law of the sines, it is very important to seek out. Or if you want to draw the circumcircle of AEF and let AP intersect at one point. For example, it is Q, and we will try to prove that P and Q are the same points. That's also available. But here, in order to make it easier, we try to use the law of the sines. So in the triangle AEP, what can we get? If we denote this as angle 1 and this is angle 2, we can have EP over sine angle 1 equals to AP over sine angle AEP, right? And also, I wrote it wrong. It is EP. And here is PF over sine angle 2. It equals to AP over sine angle AFP. So since EP and FP are the same and angle 1 and angle 2 are the same, so the sines of angle 1 and angle 2 are also the same, and we have AP equals to AP. So we have sine angle AEP equals to sine angle AFP. So we have two cases. Case 1, angle AEP equals to angle AFP. What does that lead to? Why do we want to why do we deny that AEP equals to AFP? Why don't we think it is right? The reason is that once the angle AEP equals to angle AFP, what can we have? Plus angle 1 equals to angle 2, right? Angle 1 equals to angle 2, and we have one common side, or one shared side, AP. So the triangles AEP and AFP are congruent, right? If we have the two angles AFP and AEP same, we will have these two congruent triangles. So what does that lead to? Let me write it down. That will lead to triangle APE congruent to triangle APF. Oh, it comes again. That leads to ABP collinear. It is the same as the condition that we assumed in problem 1. So that is not available. Right? It is wrong. It can't be proved. So it comes to case 2. Let me copy the diagram again. Here. So it comes to case 2. Angles AEP plus angle AFP equals to 180 degrees, and that leads to AEPF concyclic. And we can have the angle PEF equals to the angle angle 2 and equals to angle 1. So that leads to triangles PEG is similar to triangle PAE. It is very obvious after we get the concyclic quadrilaterals, right? And we can get PE square equals to PG times PA. That's another important thing we get. So we're very close to the victory. So what is the thing left? What do we try to prove? We try to prove this thing, right? So we calculate CA square plus PE square minus PA square. That equals to CA square equals to AE times AF, right? AE times AF plus PG times PA minus PA square. We try to prove that this thing it equals to 0, right? So if it is 0, what other things we should have? What are the other things we should have? Here we notice that there are two common things. AP. They are the common things AP, right? So we can write it down. AE times AF plus PA times, or we use minus PA times PA minus PG. Oh, that equals to AE times AF minus PA times, what is PA minus PA minus PG? That is AG, right? So how can we prove that? AE times AF equals to PA times AG. How can we prove that? Oh, if we get the ratios of the sides, maybe it's like AE over AG. It is equivalent to AE over AG equals to AF. No. AP over AF. So after having this, it is equivalent to the triangles AEG is similar to the triangle APF. So how to prove these two triangles similar? That's very easy. We have angle 1 equals to angle 2, and also the angle AEG equals to AG equals to angle APF. So yeah, we have proved that these two triangles are similar. So we finally get AE times AF equals to AP times AG. So this question comes to 0. So we have got CA square plus PE square equals to AP square. That's the end of the proof. So we have proved the problem successfully. Do you see that? It is maybe it is a little bit complicated to think. Not think. It is a little bit complicated to write down your thoughts or get your thoughts. But it is quite natural if you get the hints or get the points one by one. So actually, yeah, it is it is worth to be placed in the problem 1, because it is not that difficult to think or to get the idea of the solution. So that's my rate and my solution of this problem. So thank you for watching.